The Seamless World, Understanding Conflict-Free Replicated Data Types. Chapter 1, The Perils of Parallel Living, When Data Collides. Imagine you and a friend are editing the same important document simultaneously. You delete a paragraph while your friend adds a new section. What should the final document look like? Should your deletion take precedence, or your friend's addition, or should both be applied? This seemingly simple scenario is a microcosm of a massive challenge in the digital world. How do we manage data that exists in multiple places and is changed by multiple users at the same time? To understand why conflict-free replicated data types are so revolutionary, we first need to grasp the fundamental problem they aim to solve. Data conflicts in distributed systems. The distributed world we live in. Look around you, or rather, look at your digital devices. You're likely using many applications that aren't running on a single, isolated computer. When you send a message on a chat app, that message isn't just stored on your phone. It's sent to servers and then delivered to your friend's phone, which might be thousands of miles away. When you update your profile picture on social media, that image might be copied across dozens, hundreds, or even thousands of servers around the globe to ensure it loads quickly for users everywhere. This is the essence of a distributed system, a collection of independent computers that appears to its users as a single, coherent system. We interact with distributed systems constantly, whether we're aware of it or not. They are the backbone of the internet, powering everything from search engines and e-commerce sites to cloud storage and real-time streaming services. Why distribute? The benefits and a hint of the problems. The reasons for distributing data and computing power are compelling. Fault tolerance, reliability. If one computer fails, others can pick up the slack. Your data is replicated, so a hardware failure doesn't mean data loss. Think of it like having multiple copies of a vital paper document in different fireproof safes. Scalability. When a single computer can't handle the load, too many users, too much data, distributing the work across many allows the system to grow. More users, add more servers. Performance, low latency. Placing data closer to users reduces the time it takes for information to travel. A user in London interacts with a server in London, not one in Sydney, for a snappier experience. Availability. Users can access the system even if some parts of it are offline or experiencing issues. These benefits are crucial for the responsive, always-on experience we now expect. However, this paradise of distributed computing comes with a serpent: consistency. Consistency, the elusive goal. In a distributed system, consistency refers to the idea that all replicas of data, or all parts of the system, agree on the state of the data. If your bank balance is $100, you want it to show $100 whether you check it on your phone, your laptop, or at an ATM. This is intuitive when data lives in one place. But what happens when you have multiple copies? Imagine a simple counter. Let's say it starts at 0. If two users, A and B, simultaneously try to increment it, user A's client increments its local copy to 1. User B's client increments its local copy to 1. Both send their increment command to their respective nearest servers. If these servers don't coordinate perfectly, they might both believe the final value should be 1, because they each started from 0 and added 1. The result, a lost increment. The counter should be 2, but it's 1. This is a conflict. This issue arises because of something called the CAP theorem. Without getting too technical, the CAP theorem states that a distributed system can only guarantee 2 out of 3 properties simultaneously. Consistency, C, all clients see the same data at the same time. Availability, A, every request receives a response without guarantee that the response contains the most recent write. Partition tolerance, P. The system remains operational despite network failures partitioning nodes. In practical, real-world distributed systems, partition tolerance, P, is almost always a necessity. Networks are inherently unreliable. They will experience outages and delays. This means designers of distributed systems are forced to choose between consistency, C, and availability, A. Choosing consistency, C, over availability, A. If you prioritize consistency, the system might block operations or become temporarily unavailable during a network partition, until all nodes can agree on the data state. This is critical for things like banking transactions where correctness is paramount. But it means if your network goes down, you might be unable to access your money. Choosing availability, A, over consistency, C. If you prioritize availability, the system remains operational even during network partitions. But different parts of the system might temporarily show different versions of the data. This leads to what's known as eventual consistency. Eventual consistency, living with disagreement for a little while. Most modern web applications, particularly large-scale ones, opt for eventual consistency. This means that if no new updates are made to a given piece of data, eventually all reads of that data will return the last updated value. In other words, data might be inconsistent for a brief period, but it will eventually iron itself out. Think of it like a gossip network. When something new happens, not everyone knows about it instantly. Information spreads, and eventually, everyone gets the same story. This model allows for high availability and performance. However, here's the rub. If multiple users are changing the same data during that inconsistent period, you have conflicts. The dreaded data conflict, when what you see isn't what you get. Data conflicts manifest in various ways. Lost updates. As in our counter example, one update simply overwrites another without incorporating its changes. Write-write conflicts. Two users simultaneously modify the same field, leading to ambiguity about the correct final value. For instance, two people change the status field of an item from pending to approved and rejected at the same time. Concurrency issues. The order in which operations arrive at different replicas can lead to different outcomes. If user A adds hello and user B adds world to a document simultaneously, the order matters. Hello world versus world hello. Without a way to consistently resolve the relative order, the final document could be different on different machines. Traditional approaches to resolving these conflicts often involve centralization, having a single, authoritative server. This eliminates conflicts, but introduces a single point of failure and drastically limits scalability and availability. It's like having a single scribe for all documents, slow and risky. Locking, preventing simultaneous access to data. If you're editing a document, no one else can modify it until you're done. This works but can be restrictive and slow, especially in collaborative environments. Imagine being in a Google Doc and having to wait for your colleague to finish typing a sentence before you can begin your own. Merge conflicts, forcing human intervention. Version control systems like Git are famous for this. When conflicts occur, the user has to manually decide which changes to keep. While effective for code, imagine doing this for every keystroke in a collaborative document. These solutions are either too restrictive, too slow, or demand too much human effort to be suitable for the seamless, real-time collaboration that users now expect. This is precisely the gap that conflict-free replicated data types were designed to fill. They offer a fundamentally different approach, one that embraces distribution and eventual consistency, but guarantees resolution without manual intervention, no matter what. In the next chapter, we will introduce CRDTs and explore how these clever data structures achieve a remarkable feat. Allowing data to be modified simultaneously across distributed systems while consistently converging to a correct and agreed-upon state, all without a single conflict ever disturbing the harmony. Chapter 2, A New Harmony, introducing conflict-free replicated data types. We've seen the chaos that can ensue when data collides across distributed systems. The need for high availability and responsiveness has pushed us towards eventual consistency, which inevitably opens the door to conflicts. For traditional approaches, resolving these conflicts often involves trade-offs, sacrificing speed, centralization, or forcing users to manually intervene. But what if there was another way? What if data could simply resolve itself? This is the promise of conflict-free replicated data types, or CRDTs. A change in philosophy, resolving, not preventing. At their heart, CRDTs represent a paradigm shift in how we think about distributed data. Instead of trying to prevent conflicts, which is often difficult or impractical in truly distributed, high-availability systems, CRDTs embrace the idea that conflicts will happen. Their brilliance lies in their ability to resolve these conflicts automatically and deterministically, without any outside intervention or knowledge of the order in which operations occurred. Think of it like a group of musicians playing different parts of a symphony. Some traditional approaches might say, everyone must play their notes in precisely the same order, starting at the exact same moment, or the music falls apart. A CRDT-inspired conductor, however, might say, it doesn't matter who plays which note first, as long as by the end, all the notes combine to form the correct, harmonious melody. The individual notes might be played out of order from each musician's perspective, but the composition itself ensures that any combination of those correctly played notes will result in the intended music. The core principles, mathematical elegance, the magic behind CRDTs comes from applying specific mathematical properties to how data is stored and how operations on that data are designed. These aren't just abstract ideas, they are concrete rules that, when followed, guarantee convergence. The three key properties that CRDTs often rely on are commutativity. The order of operations doesn't matter. If you have operations A and B, applying a then B yields the same result as applying B then A analogy, putting on your socks then your shoes. Does it matter if you put on your left sock then right sock, or right sock then left sock? No, as long as both socks are on before the shoes. Or consider adding numbers. 2 plus 3 is the same as 3 plus 2. Associativity. When you have multiple operations, grouping them differently doesn't change the outcome. A plus B plus C is the same as a plus B plus C. Analogy. Imagine assembling furniture. If you have 3 pieces, it doesn't matter if you attach piece A to B first, then C, or if you attach B to C first, then A. The final assembled piece is the same. Idempotence. Applying the same operation multiple times has the same effect as applying it once. Analogy, flipping a light switch. If the light is off, one flip turns it on. Flipping it a second, third, or fourth time still leaves it on, assuming it was already on. Or, setting an email as read, marking it read multiple times doesn't make it unread again. When operations are designed to have these properties, independent replicas can apply changes in any order, even if some changes arrive late or are duplicated, and they will always arrive at the same final state. This is the conflict-free part of CRDTs. 2 main flavors, state-based versus operation-based. CRDTs typically come in 2 main categories, differentiated by how they propagate changes. State-based CRDTs, CVRDTs, convergent replicated data types. How they work. Each replica maintains its entire local state. When changes occur, the replica sends its entire updated state to other replicas. Other replicas receive these states and merge them with their own local state using a specific, idempotent merge function. This merge function must obey the properties we just discussed, commutative, associative, idempotent, ensuring that no matter the order of received states, the final merged state is the same. Analogy, imagine everyone in a group has a shopping list. When you update your list, you make a new copy of your entire list and give it to everyone else. They then take your list and their own, combine items from both, and create a new master list. If someone gives you the same list twice, it makes no difference because you already incorporated those items. Pros: simpler to implement in practice, as consistency relies entirely on the merge function. Updates can be batched, e.g., only push changes when the user pauses typing. Cons: can consume significant network bandwidth, especially with large states, as the entire state is sent with every change. Operation-based CRDTs, OP-CRDTs, operation-based replicated data types. How they work. Instead of sending the full state, replicas send small atomic operations, like increment, add item, delete character at position X. These operations are executed on all replicas. For this to work, operations must be designed to be commutative and idempotent, and often require additional context, like a unique timestamp or vector clock, to ensure they can be applied correctly regardless of arrival order. This additional context often helps establish a causal order, ensuring that an operation always builds on the state of previous, known operations. Analogy: instead of giving everyone your whole shopping list, you just yell out added milk or removed bread. Everyone constantly updates their own list based on these small commands. If you shout added milk twice, they only add it once because the instruction itself is idempotent. Pros: much lower network bandwidth as only small operations are sent. Can offer stronger consistency guarantees in some scenarios when operations can be ordered causally. Often preferred for real-time collaborative text editing. Cons: more complex to design and implement, as each operation must carry enough context to be applied independently and correctly, potentially requiring causal ordering mechanisms like version vectors. Despite their differences, both types of CRDTs share the fundamental guarantee: eventual strong consistency. This means that eventually, all replicas will converge to the exact same state, and that state will be correct. No manual conflict resolution, no data loss, just seamless, automatic agreement. The elegance of CRDTs lies in taking the inherent messiness of distributed systems and taming it. They don't fight the nature of networks, they work with it. They allow applications to offer highly available, responsive user experiences, even when users are offline or on flaky connections, knowing that when connectivity returns, everything will snap into place, perfectly synchronized. In the next chapter, we will dive into specific examples of CRDTs. We'll explore how simple concepts like counters and sets can be made conflict-free, and how these fundamental building blocks combine to create the robust, seamless collaborative experiences we now take for granted. Chapter 3: The Building Blocks of Agreement, States and Operations. In the previous chapter, we introduced CRDTs as a revolutionary solution to data conflicts in distributed systems. Their magic lies in carefully designed data structures and operations that automatically resolve potential clashes. We touched upon the guiding mathematical properties: commutativity, associativity, and idempotence, and the two main approaches: state-based CVRDTs and operation-based OpCRDTs. Now, it's time to see these abstract concepts come to life through concrete examples. By examining some of the simpler, foundational CRDTs, we can truly understand how they guarantee seamless agreement, even amidst chaos. Let's explore how these building blocks of agreement are constructed. The grow-only counter, G counter, counting up without conflict. Remember our problematic counter from Chapter 1, where two simultaneous increments from different users led to a lost update. A simple counter is one of the easiest ways to demonstrate CRDT principles. The grow-only counter, G counter, is a classic example of a state-based CRDT, CVRDT. As its name suggests, it can only increment grow, it cannot decrement. The idea: to prevent lost increments each actor. A user, a computer, a process that increments the counter maintains its own separate count of its contributions. How it works: instead of a single number, a G counter is effectively an array or a map. Each slot in this array corresponds to a unique actor, storing only that actor's increments. When actor A increments the counter, they increment their specific slot in their local copy of the array. When this local state is sent to actor B merges it with their own array. The merge operation is simple. For each slot in the array, take the maximum value from the corresponding slots in the two arrays being merged. For example, if actor A has 5, 2, 0, meaning a contributed 5, B contributed 2, C contributed 0, and actor B has 4, 3, 1, merging them results in max 54, max 23, max 0, 1, which is 5, 3, 1. Why it's conflict-free? The max function is inherently commutative, associative, and idempotent. Max x y is the same as max y x, commutative. Max x y z is the same as max y z, associative. And max x is just x, idempotent. Because of these properties, no matter the order in which updates arrive or how many times they are sent, the final state of the G counter will always converge to the correct total number of increments across all actors. Querying the value: to get the total count, you simply sum all the numbers in the array. This G counter solves the lost increment problem perfectly, but what if we need to count both up and down? The positive-negative counter, PN counter, when you need to increment and decrement. The positive-negative counter, PN counter, is an extension of the G counter, allowing for both increments and decrements, while remaining a state-based CRDT. The idea, instead of one G counter, a PN counter uses two G counters. One G counter tracks all increments, the P part. Another G counter tracks all decrements, the N part. How it works. When an actor performs an increment, they update their slot in the P G counter. When an actor performs a decrement, they update their slot in the N G counter. When merging states from other replicas, both the P and N G counters are merged independently using the max function, just like a regular G counter. Why it's conflict-free? Each G counter maintains its conflict-free properties independently. Since the final value is simply the sum of the positive counts minus the sum of the negative counts, the combined result is also conflict-free. Querying the value. The total counter value is calculated as sum P counter, sum N counter. PN counters perfectly demonstrate how more complex CRDTs can be built by combining simpler, well-understood CRDTs. The grow-only set, G-set, adding elements without duplicates. Another fundamental data type is a set, a collection of unique elements. How do you manage a set when multiple people are adding items concurrently? The grow-only set, G-set, is perhaps the simplest CRDT for collections. Like the G counter, elements can only be added, not removed. The idea: ensure that adding an element is idempotent and that the order of additions doesn't matter. How it works: each replica maintains its local set of elements. Adding an element, simply add the element to the local set. Merging: when states are merged, the merge function is the union of the two sets. For example, if replica A has apple, banana, and replica B has banana, orange, merging them results in apple, banana, orange. Why it's conflict-free? The mathematical operation of set union is inherently commutative. A union B is same as B union A, associative and idempotent. A union A is just A. Therefore, concurrent additions or out-of-order deliveries of updates will always lead to the same final, converged set. Querying the value. To check if an element is in the set, simply check its presence in the merged local set. The two-phase set, 2P set, adding and removing with a catch. The G-set's limitation is obvious. What if you need to remove elements? This is where the two-phase set, 2P set comes in. It's another excellent example of combining two simpler CRDTs to achieve more complex behavior, albeit with a crucial constraint. The idea: to allow removals, a 2P set uses two underlying G-sets. An add set, where elements are added. A remove set, remove a set, where elements that have been removed are stored. How it works: adding an element, the element is added to the add set. Removing an element, the element is added to the remove a set. Merging: both add set and remove a set are merged independently using the G-set's union merge operation. Why it's conflict-free and the catch. The guarantee of conflict-freeness comes from the fact that once an element is placed in the remove a set, it can never be removed from it. This means an element can be removed from the active set by being present in the remove a set, but it cannot be unremoved or re-added. This is the two-phase part. An element goes through an added phase and then can transition to a removed phase, but it cannot return to the added phase. Once removed, always removed. Querying the value. An element is considered to be in the 2P set if it exists in the add set and it does not exist in the remove a set. Expressed mathematically, active set equals add set, remove set. The 2P set is useful for scenarios where elements are permanently retired, like closing a task or banning a user. But it's not suitable for things like shopping carts, where items are frequently added, removed, and re-added. From state-based to operation-based, the same principles, different transmission. While we've primarily discussed these examples as state-based CRDTs, CVRDTs, where the full state is merged, it's important to understand that many of these basic data types can also be implemented as operation-based CRDTs, OP-CRDTs. For example, an increment operation for a counter could be sent as an OP-CRDT. Each operation would carry enough information, e.g., which actor performed the increment, such that when it arrives at a replica, it can be applied directly to the local state. The same principles of commutativity and idempotence would apply to these operations, meaning receiving an increment by actor X operation multiple times wouldn't cause an error or double count. The key difference is that instead of sending bulky states, you send lightweight operations. The choice between CRDTs and CRDTs often depends on the specifics of the application. How large is the state? How frequently do updates occur? And what are the network bandwidth constraints? These simple building blocks, counters, and sets lay the groundwork for understanding more complex and fascinating applications of CRDTs. They demonstrate that by carefully designing data structures and their associated operations to possess specific mathematical properties, we can transcend the traditional compromises of distributed systems, achieving true, effortless data consistency. In the next chapter, we'll see how these principles scale to power sophisticated collaborative experiences that we might already be using every day. Chapter 4. CRDTs in Action. Crafting Seamless Collaborative Experiences. We've explored the foundational principles of CRDTs and seen how simple data types like counters and sets can be made conflict-free. But the true power and elegance of CRDTs come to light when we observe them in action, powering the seamless, real-time collaborative experiences that many of us now take for granted. From shared documents to interactive whiteboards, CRDTs are orchestrating a new harmony in our digital interactions. The Holy Grail, collaborative text editing. Perhaps the most iconic and challenging application for conflict-free replication is collaborative text editing. Think of Google Docs, Microsoft Word Online, or Figma. Multiple users editing the same document, often simultaneously, anywhere in the world, with changes appearing almost instantly for everyone. This seems like magic, given the potential for conflicts. Consider these scenarios in a shared document: concurrent insertions. User A types banana at the start of a sentence. User B, at the same time, types apple at the start of the same sentence. What is the correct order of apple banana or bananapple? Concurrent deletions. User A deletes a paragraph. User B, concurrently, deletes a single word from within that same paragraph. Does the single word deletion apply before or after the paragraph deletion? Insertions and deletions. User A inserts a word. User B deletes the character right before User A's insertion. How does the system reconcile this? Traditional approaches to these problems are fraught with peril. Centralized locking. Locking parts of the document for editing would be too restrictive and slow for real-time collaboration. Imagine waiting for your colleague to finish a sentence before you could even type a single letter. Operational transformation, OT. For a long time, the dominant technique for collaborative editing was operational transformation. OT is incredibly complex. It requires transforming operations based on the state of the document when the operation was generated, ensuring that all operations can be applied correctly, leading to a consistent final state. It means every client needs to know what operations occurred, when, and in what order, and they need to transform incoming operations to correctly apply them to their divergent local state. While powerful, OT systems are notoriously difficult to implement, debug, and scale. They are sensitive to network latency and packet loss, often requiring strong guarantees about message ordering, which is hard to achieve in truly peer-to-peer or offline scenarios. CRDTs offer a compelling alternative to OT, simplifying the underlying model by guaranteeing convergence without complex transformations. How CRDTs tackle collaborative text. The core idea behind using CRDTs for text editing is to treat each character in the document as an independent element that can be added or removed. To achieve automatic conflict resolution, each character needs a globally unique and stable identifier, and the relationships between characters, their order, must also be handled conflict-free. Here's a simplified look at how it works. Unique character identification. When a character is inserted, e.g., it's not just it's with a unique ID attached, often composed of the user's ID and a timestamp, or a more sophisticated hierarchical ID to help with ordering. This ID persists for the lifetime of that character. Relative ordering. Simply giving characters unique IDs isn't enough. We need to know their order. CRDTs use clever mechanisms to maintain this order without a central authority. For instance, when you insert a character between two existing characters, its unique ID is generated in a way that, even if many users insert characters at the same spot. Concurrently, the system can deterministically decide their final relative order. This often involves algorithms that generate positions between any two existing positions, allowing for infinite insertions without reindexing. Addition and deletion as grow-only operations with a twist, adding characters. This is effectively a grow-only set. Each character, with its unique ID, is added to the document's set of characters. Since character IDs are unique and their relative positions are determined robustly, concurrent insertions simply add characters, and their positions will eventually converge consistently. Deleting characters. This is where it gets interesting. Instead of truly deleting a character, which would be challenging to synchronize if another user also happens to be editing that character, CRDT-based text editors often use a mechanism akin to a two-phase set or tombstoning. When you delete a character, it's not removed from the underlying data structure. Instead, it's marked as deleted or added to an out-of-document set. Other replicas eventually receive this delete operation, which simply changes the state of that unique character ID, and they also mark it as deleted, removing it from the user's view. An important property here: a character that has been marked for deletion cannot be magically undeleted by another concurrent operation. This ensures convergence. What you see is the set of all added characters, excluding those which have been marked as deleted. The beauty of this approach is that the state of the document, the collection of characters and their relative positions, is a CRDT itself. Any set of operations, applied in any order, will always converge to the same final document. This makes peer-to-peer collaboration, offline editing, and resilience to network outages much simpler to implement compared to OT. Beyond text, other collaborative applications, the principles applied to text editing, extend to a vast array of other real-time collaborative applications. Collaborative whiteboards and design tools. Drawing lines, shapes, or placing images can be modeled as adding elements to a shared canvas, GSet. Moving or resizing shapes can be handled by creating unique IDs for each object and using a last write wins, LWW, register CRDT for properties like X, Y coordinates, width, height, or color. The last write is determined by a timestamp associated with the operation, ensuring the most recent change takes precedence. Deleting objects works similarly to text deletion, marking them as removed. Gaming. Updating player scores. RPN counter is perfect for this. Tracking inventory items, a GSet for items you've picked up. Synchronizing game state components. CRDTs can be used for things like health bars, ammo counts, or even player positions, especially in games that can tolerate eventual consistency for some elements. Shared calendars and task lists. Adding an event or task, GSet, marking a task as complete, similar to our 2P set or a flag-based LWW register on the task status. Assigning tasks to users, potentially using LWW registers for assignee fields. Decentralized applications, Web3 blockchain. CRDTs are a natural fit for decentralized applications, DApps, where there's no central server and participants need to maintain consistent states. They can be used for shared data in decentralized social networks, shared databases, or even elements within smart contracts that need off-chain synchronization. In essence, any application where multiple users need to concurrently modify shared data in a way that always converges to an agreed-upon state is a candidate for CRDTs. They simplify the development process of distributed software by offloading the complex conflict resolution problem to the data structures themselves. We've seen how CRDTs shift the focus from preventing conflicts to automatically resolving them, opening up a world of possibilities for seamless digital collaboration. While this chapter provided a conceptual overview, the next one will delve deeper into more advanced CRDTs and the clever tricks they employ to handle even more complex data types and scenarios. Chapter 5. Beyond the basics, advanced CRDTs and their clever tricks. In the preceding chapters, we demystified the core idea of conflict-free, replicated data types through foundational examples like counters and sets. We've seen how their mathematical properties allow them to handle concurrent operations without conflict. But the real world is often more complex than simply counting or adding distinct items. How do CRDTs handle scenarios where values change, elements are truly removed and re-added, or where efficiency becomes paramount? This chapter delves into some more sophisticated CRDTs and the ingenious design patterns that enable them to tackle these nuances, demonstrating their versatility and robustness. The last right wins, LWW register. Simple assignment with a condition. Sometimes, you don't need a complex merging strategy for a value. You simply need to ensure that the latest change is the one that sticks. This is where the last right wins, LWW register comes into play. The idea, an LWW register stores a single value, just like a variable in a programming language. When multiple parties try to change that value concurrently, the system decides on a winner based on a timestamp. How it works. Each time the value in an LWW register is updated, it's associated with a timestamp, e.g., the time the update occurred. When two replicas are merging their states, if they both have different values for the register due to concurrent updates, the value with the latest timestamp wins. If timestamps are identical, a rare but possible occurrence given high-resolution clocks. An arbitrary tie-breaking rule, like comparing the IDs of the nodes that made the change, is used to ensure a deterministic outcome. Why it's conflict-free. The rule, the latest timestamp wins, makes the operation commutative, associative, and idempotent. Applying a change with an older timestamp has no effect if a newer one already exists. Applying the same change twice, with the same timestamp, also has no effect. Limitations. LWW registers are simple and efficient, but their simplicity is also their limitation. They are only suitable for values where the concept of latest is correct makes sense. For instance, if you and a friend simultaneously update a shared note, LWW might discard one of your changes. It's often used for things like the current position of an object on a whiteboard, where only the final position matters, or a profile picture, where the latest uploaded image overrides previous ones. In cases where all changes are valuable, such as collaborative text, an LWW register alone is insufficient. The observed remove set, OR set, re-adding what was removed. Recall the two-phase set, 2P set from the last chapter. Once an element was put into the remove set, it could never be re-added. This makes sense for some scenarios but is very restrictive for others, like a shopping cart where you might add an item, remove it, and then decide to add it again. The observed remove set, OR set, overcomes this limitation by making a clever distinction between the addition of an element and the removal of a specific instance of that element. The idea. Instead of simply saying, element X is in the set, or element X is removed, an OR set tracks unique tags for each time an element is added. To remove an element, you specify which specific addition you are undoing. How it works. Adding an element. When an element, e.g., apple, is added, it's inserted into an internal set along with a unique tag or ID for that specific addition, e.g., apple tag 1. This tag is typically a combination of the replica's ID and a local counter, guaranteeing its uniqueness. Removing an element. To remove apple, the replica doesn't just say remove apple. Instead, it identifies which tags associated with apple it intends to remove. It then adds these specific tags to a separate removed tags internal set. Merging. When merging two OR set states, it performs the union of all element, tag pairs from both sides. It also performs the union of all removed tags from both sides. Why it's conflict-free. An element is considered present in the set only if its element, tag pair exists in the add set and that specific tag has not been recorded in the remove tag set. Both additions and removals propagate reliably through set unions. If you remove an item and someone else adds it back before your removal propagates, their addition will have a new tag. Your removal operation specifically targets the old tag, leaving the new one unaffected. This allows for re-addition. Analogy. Imagine a library where every book has a unique accession number when it's added. To remove a book, you don't just say remove Pride and Prejudice. You say remove Pride and Prejudice with accession number 12,345. If someone else later adds another copy of Pride and Prejudice, it gets accession number 67,890. Your removal only affects 12,345. The OR set is a powerful CRDT, essential for collaborative applications like shopping carts, task management, or shared lists where items are frequently added, removed, and potentially re-added. Delta CRDTs, sending only what's new. Our discussion of state-based CRDTs, CVRDTs, mentioned a drawback. Sending the entire state can be inefficient, especially for large data structures or frequent small updates. This is where Delta CRDTs offer a clever optimization. The idea: instead of sending the full local state, a Delta CRDT allows a replica to compute and send only the delta, the minimal set of changes that occurred since the last known common state or since the last reconciliation. How it works: when a replica makes a change, it creates a small object representing that change, the delta. This delta is itself a CRDT, capable of being merged with other deltas. Replicas then exchange these compact deltas. When a receiver gets a delta, it applies it to its local state using a specialized merge function for deltas. This local state will then converge with the sender's state without needing to exchange the full, potentially large, base state. Benefits: significantly reduces network bandwidth, making synchronization faster and more efficient, especially over slower or constrained networks. It allows for more granular updates, improving responsiveness. Analogy: instead of sending your entire updated shopping list to everyone, you just shout, "I added milk and removed bread." Everyone then applies those small, efficient changes to their own list. Many advanced CRDTs, including OR sets, have delta-capable versions, allowing them to benefit from this efficiency. Causality tracking, vector clocks and dot clocks. For OP-CRDTs, where operations are sent individually, ensuring they are applied correctly regardless of network latency requires a sophisticated way to understand the causal relationship between operations. What if Operation A happens before Operation B, but B arrives at a replica first? You don't want B to be applied if it logically depends on A, which hasn't arrived yet. The idea: casual ordering mechanisms ensure that operations are applied only after all causally preceding operations have been applied. Vector clocks. A common technique is vector clocks. Each replica maintains a vector, an array of counters, one for every replica in the system. When a replica performs an operation, it increments its own counter in its vector. When sending an operation, it sends its current vector clock along with the operation. When receiving an operation, a replica compares the incoming vector clock with its own to determine if the operation can be applied immediately or if it must wait for other, causally prior operations to arrive. Dot clocks, more specifically for CRDTs, dot clocks, or version vectors, are often used. A dot typically combines a replica ID and a local counter. Each operation is associated with a specific dot. This allows replicas to track which operations they have already seen and which they are missing, ensuring they don't apply an operation twice or apply an operation out of causal order. Clever trick. These mechanisms allow OP-CRDTs to deliver their conflict-free guarantees even when network messages are delayed, duplicated, or reordered, by ensuring that the meaning of the operation is preserved. The accumulation problem, tombstones and garbage collection. A common trick in many CRDTs, particularly those allowing removals like OR sets or collaborative text CRDTs, is the concept of a tombstone. When an element is removed, it's often not truly purged from the data structure. Instead, it's marked as deleted or its deletion tag is added. Why tombstones? These tombstones are crucial for correctness. They prevent resurrection. If a replica that hasn't yet seen the removal operation tries to re-add the item or applies an old add operation, the presence of the tombstone ensures that the item remains deleted across all replicas. Without tombstones, concurrent operations could lead to different replicas converging to different states. The problem: tombstones accumulate over time. For a collaborative document edited for years or a frequently updated set, the memory occupied by these deleted but still necessary markers can grow indefinitely. This impacts performance, memory footprint, and the size of states or deltas being transmitted. Solutions: This is an active area of research and implementation challenge. Compaction garbage collection. Periodically, when all replicas are known to have seen all relevant operations up to a certain point, a global garbage collection can occur where tombstones that are no longer needed, because no new conflicts could arise involving them, are pruned. This often requires careful synchronization and can be complex to implement in a truly decentralized manner. Specialized CRDTs. Some CRDTs are designed to be garbage collectible by design, often by incorporating mechanisms that allow certain historical data to be safely discarded without jeopardizing conflict freedom. From ensuring simply picking the latest value, to handling dynamic sets that allow elements to come and go, to optimizing network traffic, and managing the long-term health of data structures, advanced CRDTs incorporate a rich tapestry of theoretical and practical solutions. Their elegance lies in how they bake conflict resolution directly into the data structure's definition, shifting the burden from complex coordination protocols to the inherent properties of the data itself. In the next chapter, we'll turn our attention from how CRDTs work to where they are being widely used, showcasing their foundational role in many modern applications and technologies. Chapter 6. The backbone of modern apps. Where CRDTs shine. We've explored the theoretical underpinnings and clever mechanisms of CRDTs. Now, it's time to see where these innovative data structures are quietly powering the seamless digital experiences we encounter every day. CRDTs are increasingly forming the hidden backbone of applications that demand real-time collaboration, offline capabilities, and resilience in complex, distributed environments. 1. Collaborative productivity tools. The new standard. The ability for multiple people to work on the same document, spreadsheet, presentation, or design file simultaneously has become an expectation, not a luxury. While we briefly touched on text editing, CRDTs support the broader category of collaborative productivity tools. Google Docs, Microsoft Office Online. While the exact implementations can be proprietary and complex, modern collaborative text editors often leverage CRDT-like principles. As previously discussed, the ability for characters to be inserted or deleted independently, and for those operations to always converge to the same sequence of text, whether or not users are connected to a central server at all times, is a defining feature. Figma, Milanote, Excalidraw. These real-time design and whiteboard tools allow teams to draw, move objects, type notes, and brainstorm together. Each shape, line, or piece of text on the canvas can be modeled as a CRDT. For instance, an object's position might be an LWW register. Its properties, color, size could be other CRDTs, and its existence on the canvas governed by an OR set. This ensures that concurrent edits, like two users moving the same object or one changing its color while another resizes it, eventually harmonize into a single, correct state. Notion, Coda, Obsidian Sync. These tools combine elements of documents, databases, and wikis, maintaining consistency across complex, interlinked data structures while allowing real-time collaboration and often offline access is a massive challenge. CRDTs offer a powerful primitive for handling the concurrent edits to individual blocks, properties, or database entries that make up these dynamic documents. Why CRDTs shine here? The primary benefit is the fluid, real-time user experience. Users don't have to worry about saving, locking, or merging. Changes appear instantly, and the system handles the complexities of concurrency behind the scenes, ensuring data integrity without needing a constant, perfect connection to a central server. This enables truly responsive, always available collaboration. 2. Offline-first applications, bridging the connectivity gap. Many modern mobile and web applications are designed to be offline first. This means they function fully even without an internet connection, synchronizing changes seamlessly once connectivity is restored. CRDTs are a natural fit for this architecture. Note-taking apps, mobile. Imagine taking notes on a plane. You want to keep working even without Wi-Fi. When you land, your notes automatically sync with your desktop version and any cloud backups. If you added points on your phone and deleted others on your laptop while offline, CRDTs enable these independent changes to merge harmoniously. Field service applications. Technicians in remote areas might fill out forms, log data, or update statuses from ruggedized tablets. Connections can be spotty. With CRDTs, data collected offline can be confidently merged back into the central system when connectivity is reestablished, without manual reconciliation being required for common operations. Point-of-sale (POS) systems. A small cafe's POS system might lose internet connection during a busy lunch rush. It needs to continue processing orders and sales. CRDTs could help keep track of inventory changes, sales totals, or customer loyalty points, merging all transactions once the network is back online. Why CRDTs shine here? CRDTs provide robust eventual consistency for intermittent connectivity. They decouple the act of making a change from the act of synchronizing it, allowing users to remain productive even when disconnected. The built-in conflict resolution means that when devices reconnect, their local states can be merged automatically and correctly, eliminating data loss or manual synchronization failed messages. 3. Decentralized systems, Web3 and beyond, building trustless consensus. In the burgeoning space of decentralized applications, DApps, where there's no single central authority, agreeing on a shared state across many independent nodes is critical. While blockchains provide fundamental consensus for state transitions, CRDTs can sit on top or alongside managing data that doesn't need to live directly on a blockchain. Peer-to-peer collaborative networks. Imagine a decentralized social network or a file-sharing system where users modify shared data without a server mediating. CRDTs can manage user profiles, friend lists, or the metadata of shared files, allowing independent updates to converge correctly across many peer nodes. Decentralized databases. Efforts like IPLD, interplanetary linked data, and various distributed database projects explore using CRDTs to build consistent data storage layers without requiring a centralized coordinator. This is crucial for truly resilient and censorship-resistant applications. Edge computing and IoT. In environments with countless small, independent devices, like smart home sensors or industrial IoT gear, CRDTs help these devices maintain a consistent view of local states or aggregate data, even with limited bandwidth and intermittent peer-to-peer communication. Why CRDTs shine here? CRDTs provide a pathway to trustless, automatic data consistency without a central coordinator. They are ideal for systems where participants operate independently but need to agree on shared data, reducing reliance on centralized servers, improving censorship resistance, and enabling true peer-to-peer interactions. 4. Gaming, synchronizing the virtual world. In many online games, particularly those with real-time elements, maintaining a consistent game state across multiple players and servers is paramount. Player inventories and scores. For games where players can pick up items, gain experience, or accumulate currency, CRDTs like OR sets, for inventory, and P encounters, for scores, can ensure that independent actions by players or server shards eventually result in a correct, converged state. Lost items or incorrect scores due to network latency would be frustrating. Shared world elements. In massive multiplayer online games, MMOs, or real-time strategy games, actions by one player can affect the environment for others, while core game logic often relies on more rigid consistency models. Certain elements, such as the state of a minor objective or the results of certain non-critical player interactions, could potentially be managed with CRDTs to reduce synchronization overhead and improve responsiveness. Why CRDTs shine here? For certain aspects of game state, CRDTs offer high availability and responsiveness with eventual consistency. They can reduce the burden on central game servers and minimize frustrating lag or desynchronization effects for users, allowing for smoother, more dynamic gameplay experiences. In summary, CRDTs bridge the gap between the need for distributed, highly available applications and the inherent challenges of data consistency. They are not a silver bullet for every type of data or every consistency requirement. For example, financial transactions demanding immediate, strong consistency, like bank transfers, would likely still use traditional database strict consistency models. However, for a vast and growing range of applications centered around collaboration, offline capability, and decentralized architecture, CRDTs are proving to be an elegant, powerful, and increasingly indispensable tool in the modern developer's toolkit. The benefits are clear: reduced development complexity for distributed systems, improved user experience through real-time responsiveness and offline access, and the enablement of truly decentralized architectures. Yet, as with any powerful technology, CRDTs come with their own set of considerations and challenges. We will delve into these in the next chapter. Chapter 7: Navigating the Nuances, Challenges and Considerations. By now, you're likely impressed by the cleverness and power of conflict-free replicated data types. They offer an elegant path to building highly available, responsive, and collaborative applications without the headache of manual conflict resolution. However, like any sophisticated technology, CRDTs are not a silver bullet. Understanding their trade-offs, challenges, and limitations is crucial for successful implementation and realistic expectations. 1. The accumulation problem. Data growth and tombstones. One of the most persistent practical challenges with many CRDTs, particularly those that allow elements to be removed, like the OR set or collaborative text CRDTs, is the accumulation of historical data, or tombstones. As discussed in Chapter 5, for an element to be truly conflict-free in its removal, its existence, or the record of its deletion, often needs to persist for some time, or even indefinitely. This is because a replica that was offline might re-add an old version of the element unless it's explicitly told that the element was deleted. These markers, or tombstones, ensure that once an element is removed, it stays removed even if old add operations for it suddenly reappear. Impact: this leads to ever-growing data structures. Over time, the size of the CRDT state can become substantial, consuming more memory, requiring more storage, and increasing the network bandwidth needed for full state synchronization, even though Delta CRDTs mitigate this somewhat. For a collaborative document edited for years by hundreds of people, the hidden tombstones could vastly outweigh the actual visible content. The garbage collection dilemma. Safely garbage collecting these tombstones is a complex problem. You can only discard a tombstone when you are absolutely certain that all relevant replicas have processed the deletion, and there's no possibility of an old add operation for that specific item reappearing. This requires some form of global consensus, or stabilization point, which can be hard to achieve in truly decentralized, peer-to-peer systems without a central coordinator. Research into efficient and robust garbage collection for CRDTs is an active area, but it remains a significant hurdle for long-lived, high-volume applications. 2. Performance considerations. CPU and memory footprint. While CRDTs offer significant benefits in terms of reliability and data consistency, they can introduce their own performance overheads. Memory. Complex CRDTs, especially those that track detailed causality, like some text editing CRDTs that store metadata for every character or all historical operations, for OP-CRDTs, can be memory intensive. Even simple counters, when implemented as per-actor contributions, consume more memory than a single integer. CPU. Merging operations for complex CRDTs or processing incoming deltas requires computational power. While typically optimized for very high-throughput systems or devices with limited resources, this processing can add latency or consume significant battery life. Network. Even with efficient Delta CRDTs, managing the communication of operations, vector clocks, and occasional full-state synchronizations still incurs network overhead. 3. Design and implementation complexity. While the idea of conflict-free data is elegant, the precise mathematical and algorithmic details required to guarantee it can be intricate. Picking the right CRDT. There isn't just a CRDT, there are families of CRDTs, each with different properties, trade-offs, and suitability for specific use cases. Choosing the correct CRDT, e.g., OR set Vs, 2P set, or designing a composite CRDT by combining simpler ones requires a deep understanding of their behavior. Implementing from scratch, building CRDTs correctly, ensuring all invariants and mathematical properties are maintained, is challenging and error-prone. Even experienced distributed systems engineers can make subtle mistakes that lead to divergence. Tooling and libraries. While the CRDT ecosystem is growing, it's not as mature or feature-rich as traditional database ecosystems. Ready-to-use, production-grade CRDT libraries and frameworks are available, but they are fewer and require more hands-on knowledge than, say, incorporating a standard SQL database. 4. The learning curve for developers. CRDTs represent a fundamental shift in how developers think about data and concurrency. Paradigm shift, moving from a traditional read modify write with locks or transactional model to an append-only, merge-only model requires a different mental model. Operations cease to be destructive updates and become additive historical facts that are eventually reconciled. Debugging challenges. Debugging issues in distributed, eventually consistent systems is inherently difficult. When a CRDT state diverges, it can be extremely challenging to trace the sequence of events and operations that led to the inconsistent state across multiple independent replicas, especially if they operated offline for periods. The lack of a single source of truth makes traditional debugging tools less effective. 5. When CRDTs are not a fit, strong consistency demands. It's important to remember that CRDTs offer eventual strong consistency. This means that while they guarantee all replicas will eventually agree on the same value, there can be periods where different replicas show different values. For certain critical applications, such as financial transactions, e.g., credit card payments, debiting a bank account, stock trading, immediate and absolute consistency is non-negotiable. You cannot tolerate a scenario where two users see different account balances, even for a moment, or where a payment fails to register due to eventual consistency. These scenarios typically require strong consistency. All clients see the same data at the same time. Linearizability. Operations appear to happen instantaneously and in a single, well-defined order. Transactions. Atomic operations that either fully succeed or fully fail. These properties are usually achieved through distributed consensus algorithms, like Paxos or Raft, or centralized transaction managers, which prioritize consistency over availability during network partitions, recalling the CAP theorem. While CRDTs might complement such systems, e.g., for non-critical parts of the application, they cannot replace the core transactional engine where absolute, immediate consistency is paramount. Conclusion. Informed application. The challenges outlined above do not diminish the value or revolutionary nature of CRDTs. Rather, they highlight the importance of choosing the right tool for the right job. By understanding the practical implications of data growth, performance overheads, implementation complexities, and the learning curve, developers and architects can make informed decisions. CRDTs excel in environments demanding high availability, responsiveness, and collaborative features, especially in the face of unreliable networks or offline operations. When applied judiciously and with an awareness of their characteristics, CRDTs offer a powerful and elegant pathway to building a more robust, resilient, and seamless digital future. The next chapter will look at the ongoing innovations and the future trajectory of CRDTs. Chapter 8, The Future is Conflict-Free, Innovations and What's Next. We've journeyed through the intricacies of conflict-free replicated data types, from their foundational principles to their practical applications and inherent challenges. It's clear that CRDTs offer a compelling vision for a more robust, responsive, and distributed digital world. But the story doesn't end here. CRDTs are a relatively young field of research, and the pace of innovation is accelerating. The future promises even more sophisticated and wider-reaching applications. Let's look at some of the key areas of innovation and what we can expect next from the world of conflict-free data. 1. Addressing the accumulation problem, smarter garbage collection. As highlighted in the previous chapter, the accumulation of tombstones is a significant practical hurdle for long-running, high-volume CRDT applications. Researchers and developers are actively pursuing more efficient and automatic garbage collection (GC) strategies. Periodical compaction. One approach involves developing protocols for periodical compaction of CRDT states. This would allow systems to safely discard outdated tombstones and historical metadata, once all replicas are guaranteed to have processed the relevant operations. The challenge here is orchestrating these global GC cycles in a truly decentralized system without introducing central points of failure or temporary inconsistencies. Contextual GC. Instead of global GC, some research focuses on contextual garbage collection, where parts of the CRDT state can be pruned if specific conditions are met, e.g., all known replicas have seen a certain operation, or a certain period of inactivity has passed for a specific element. New CRDT designs. Future CRDT designs might incorporate GC mechanisms directly into their definition, allowing for more automatic and distributed pruning of history without the need for complex external coordination. Solving the garbage collection problem effectively will significantly improve the long-term scalability and performance of CRDT-powered applications. 2. Standardized CRDTs and interoperability. For CRDTs to reach their full potential, especially in decentralized and peer-to-peer contexts, there's a growing need for standardized CRDT definitions and widely adopted protocols for their synchronization. Formal specifications. Researchers are working on more rigorous and formal specifications of CRDTs, making it easier for different implementations to be truly compatible. This goes beyond the conceptual understanding and delves into precise mathematical definitions of operations and merge functions. Wire protocols. Standardized wire protocols for transmitting CRDT updates, deltas, would enable different applications and platforms to interoperate seamlessly. Imagine a scenario where a collaborative document edited in one application could be opened and edited in another, even if they use different underlying CRDT libraries, because they adhere to common communication standards. Ecosystem maturity. As the ecosystem matures, we will see more robust, optimized, and developer-friendly CRDT libraries and frameworks emerge across various programming languages, accelerating adoption and reducing implementation complexity. 3. Integration with WebAssembly and edge computing. WebAssembly, WASM, is a low-level bytecode format that allows code written in languages like Rust, C++, or Go to run efficiently in web browsers and other environments, like serverless functions or edge devices. Powerful client-side logic. Combining CRDTs with WebAssembly opens up exciting possibilities for client-side applications. Complex CRDT logic, traditionally residing on servers, can run directly in the browser with near-native performance. This enables even richer offline-first capabilities and more sophisticated real-time collaboration directly in the user's hands. Edge devices and IoT. For devices at the edge of the network, think smart sensors, industrial controllers, or even smart home appliances. CRDTs offer a way to maintain local consistency and synchronize with other devices or cloud services. WebAssembly could provide the runtime for efficient CRDT processing on these constrained devices, allowing for localized decision-making and reduced reliance on constant cloud connectivity. 4. Hybrid consistency models, the best of both worlds. While CRDTs excel at eventual consistency, some applications still require moments of strong consistency, e.g., checking if a user has sufficient funds before allowing a purchase. Future systems will likely see a rise in hybrid consistency models. CRDTs for collaboration, transactions for commit. This approach combines the best of CRDTs for real-time collaborative editing with a transactional layer for committing a final, strongly consistent version of the document. For instance, a drawing application might use CRDTs for freeform sketching, but then use a traditional distributed transaction when a user clicks Save or Publish, ensuring the final state is globally consistent. CRDTs for conflict resolution, consensus for ordering. In truly decentralized systems, CRDTs can handle data updates, while separate consensus mechanisms, like those used in blockchains, could simply agree on the order in which these conflict-free operations should be applied across the entire network. This separates the difficult problem of what order did things happen in from how do we resolve the conflict if they happened concurrently. 5. Formal verification and reliability. Given the subtle complexity of distributed systems and CRDTs, there's a growing push for formal verification. This involves using mathematical methods to prove that a CRDT implementation will always behave as expected and guarantee convergence, even under every possible adversarial condition: network failures, reordering messages, arbitrary delays. Increased trust. Formally verified CRDTs would provide an unprecedented level of trust and confidence, making them suitable for even more mission-critical applications where correctness is paramount. Automated testing and generation. Research might lead to tools that can automatically generate CRDTs or test their properties, simplifying their design and ensuring their correctness before deployment. The road ahead. The vision of a ubiquitous, conflict-free digital world is becoming increasingly tangible. CRDTs are not merely a theoretical curiosity, they are a vital component in realizing this future. From enhancing existing collaborative tools to enabling truly decentralized applications, from powering offline-first experiences to strengthening the backbone of edge computing and IoT, CRDTs are a technology poised for mainstream adoption. As the internet becomes more pervasive and our reliance on collaborative, real-time applications grows, the demand for robust, self-healing data structures will only intensify. The innovations in CRDTs promise to simplify the lives of developers, reduce the frustrations of users, and allow us to build a more resilient and seamless digital future where data collisions are not a source of chaos, but merely a temporary, automatically resolved imperfection on the path to harmony. Conclusion: building a more resilient digital future. We live in a world defined by connection. From the moment we wake up and check our phones, throughout our workday collaborating with colleagues, and into our evenings engaging with friends and entertainment, our lives are interwoven with digital systems. Crucially, almost all these experiences are built upon distributed data information that lives and breathes across countless servers, devices, and networks around the globe. This very distribution, while offering immense benefits in terms of reliability, scalability, performance, and availability, carries a fundamental challenge. How do we keep all these independent copies of data consistent when multiple parties are changing them at the same time? For too long, the answer often involved compromises. Sacrificing responsiveness for strict consistency, relying on complex and fragile central servers, or burdening users with manual conflict resolution. The result was often a digital experience that, while powerful, could occasionally feel brittle, frustrating, or slow. This book has introduced you to conflict-free replicated data types, or CRDTs, as an elegant and transformative answer to this dilemma. We've seen how CRDTs shift the paradigm from preventing conflicts to resolving them automatically and deterministically. By embedding mathematical properties like commutativity, associativity, and idempotence into their very design, CRDTs allow distributed systems to operate asynchronously, accepting concurrent changes from anywhere, at any time, and yet guarantee that all replicas will eventually converge to the same, correct state. They are the architects of a silent, sophisticated harmony in the unseen orchestra of data. We explored their core mechanisms, understanding how state-based CVRDTs merge entire snapshots and operation-based OpCRDTs propagate discrete changes, both adhering to the same set of principles to prevent divergence. We saw how simple building blocks like G-counters, PN-counters, G-sets, and OR-sets could manage concurrent updates without a single hiccup. The true magic of CRDTs came alive when we discussed their real-world impact. They are the unsung heroes behind the seamless experience of collaborative text editing platforms, allowing multiple users to type simultaneously without overwriting each other's work or causing frustrating merge conflicts. They are foundational for offline-first applications, ensuring that changes made during periods of disconnection automatically sync and resolve when connectivity returns. Moreover, CRDTs are becoming indispensable in the burgeoning world of decentralized systems, providing a robust layer for managing shared data without relying on a central authority, powering transparent, peer-to-peer interactions. From collaborative design tools to certain aspects of online gaming, CRDTs are quietly reshaping our digital landscape. Of course, no technology is without its nuances. We honestly address the challenges inherent in CRDTs, such as the accumulation of tombstones and the complexities of garbage collection, their performance considerations, and the learning curve for developers grappling with a new concurrency model. We also clarified that CRDTs, designed for eventual consistency, are not a replacement for strong consistency models where immediate, absolute agreement, as in critical financial transactions, is paramount. Yet, despite these considerations, the trajectory of CRDTs is unequivocally upward. The ongoing innovations in smarter garbage collection, the push for standardization and interoperability, and their deeper integration with emerging technologies like WebAssembly and edge computing, all point to a future where CRDTs are not merely a specialized solution, but a ubiquitous component of robust distributed software. The increasing demand for real-time collaboration, resilient offline capabilities, and truly decentralized applications ensures their continued evolution and adoption. The digital world we inhabit is becoming ever more interconnected and dynamic. The ability for diverse platforms and countless users to interact with shared data flawlessly, without the friction of conflicts or the fragility of centralized bottlenecks, is no longer a luxury. It is a necessity. Conflict-free replicated data types offer us a powerful lens through which to simplify the complexity of this distributed future. They empower developers to build applications that are not only faster and more reliable, but also inherently more resilient and user-friendly. By understanding how CRDTs work, why they are needed, and where they are heading, you are now equipped to appreciate the invisible harmony that orchestrates so much of our digital lives. You are also better prepared to contribute to building a more robust, decentralized, and truly seamless digital future. One where data collisions are no longer a source of chaos, but merely a testament to the elegant solutions engineered beneath the surface.